So what we are doing here is sequential comparison of predictive ability. So we're going into the direction of doing time uniformly. And this is joint work with Jan-Lukas Wermuth, who's a PhD student in Frankfurt, who did, I would say, most of the hands-on work with the project, and Johanna Ziegel from ETH. So let's jump in with a very easy motivating example. What we have is we want to forecast, or we want to compare two forecasting models, and I chose two standard models for volatility forecasting, historical simulation. So what it does, it's barely visible. Okay, so you simply take the empirical variance of the past 250 trading days, not a that good forecasting model, and a gauge model or TRR gauge model here, that's a bit more sophisticated. And we want to know which model has better forecasts out of sample. So what we do, the usual approach would be, we estimate both models, the parameters on the training sample, compare or compute predictions in a rolling fashion, evaluate predictions on a test sample, and then run the famous Diebold Mariano. So let's do that. And we start, I forgot to put in the year, we start in 2020, a bit after COVID. So historical simulation is pretty flat. And the reason for that is that we had these big outliers in COVID. So the variance in COVID, or this big variance in COVID, stabilized that. And then we have the gauge model. And you already see, and so what we plot here is the financial returns in gray, the standard deviation, so that it has the same scale forecast, in red for the gauge model, and in blue for the historical simulation. Now, well, TRR gauge looks much better. We all know that. Now, after 100 days, we're quite fast. We run a Diebold Mariano test and get a t-statistic of -1. So we cannot reject. That's too bad. Then let's wait another 50 days. Do the same thing again. We have a t-statistic of -2.7. Now we reject. Are we allowed to do that? Formally, no. I mean, we could, of course, correct the significance levels by Bonferroni or something, but this is not that nice, especially if you want to do that every day, every trading day. So we would like to develop inference methods that allow for. Now, to illustrate what goes wrong with the Diebold Mariano test, let's say we simulate AR1 loss differences with standard normal error terms. Under this DGP, so delta I are the loss differences. Under that delta I, the null hypothesis of Diebold Mariano is satisfied, so we should not reject in more than 5% of the instances. Now, what we can do, we can not only do the Diebold Mariano test, but we can give confidence intervals. So what I plot here, that's the true mean, and this is the Diebold Mariano confidence interval. So you can invert the test, or it's just a t-test to get a t-test confidence interval, and you plot that over time. Now we see under the null we have this rejection here. Some rejections are fine, but they shouldn't accumulate too much. So if we look at the cumulative miscoverage rates, if you peek at the data every day, we see that in the beginning we're just above 5%. That's probably a problem with the Hug estimator, that it's not perfectly consistent. And then the cumulative miscoverage inflates to even over 50%. So in over 50% of the cases, at some point, you have such rejections. And this is not what we want to have. So what we want to have, if we do time uniform inference or sequential testing, is we want that this cumulative miscoverage rate stays below that 5% line. And so we have two options as statisticians. We can tell other researchers not to peek at. Don't peek at the data. That's one option. But it would be even better if we could develop methods that allow for doing that. Because maybe a researcher even wants to look at the data and wants to have conclusions as soon as possible. Because in that instance, having rejections after 150 days is quite nice. And you don't have to wait for, let's say, 5 years till you run your test one single time. Okay, so what we do, our main contributions in that paper are, we develop a DM-style test that allows for continuous monitoring. So you're allowed to run that test every trading day. And what puts us above, I would say, existing contributions, or what makes our contribution unique, is that it applies in a very general setting, in the sense that existing contributions rely on bounded loss differences or martingale dependent stuff that doesn't always hold for the loss difference. So we'll come to that later. And what we do, we rely on so-called asymptotic confidence sequences. That's a publication from Warby Smith et al. In 2024 in the Annals. And they already propose asymptotic confidence sequences, what we use. However, we still have some theory that we add here. So we extend the proofs to a general time series setting with an Hug estimator, so where we need a long-term variance estimator. We have asymptotic coverage proofs. We do one-sided asymptotic confidence sequences. For Diebold Mariano, one-sided is straightforward. Here it's a bit more involved, but it's too difficult. And we do both conditional and unconditional predictive ability. So here's a preview on our method. I already showed you the black Diebold Mariano confidence interval. Now our confidence sequence is a bit wider. That's the red one. And what you see is that Well, the cumulative miscoverage rate stays below 5%. Now, how does it look like? The sequence we're proposing is the sample mean, time t is the running index that you increase, plus minus a variance estimator or standard deviation estimator S in standard confidence intervals. And the big difference is that instead of the standard normal quantile, we have this term which is a bit more involved. And we'll come to that. And now the guarantee that we have is in fact this guy in the end. So what we have is the probability that the truth, and the truth is that delta t is inside the confidence sequence, CT, that is 1 minus alpha. However, for all t larger than some m. So as that m, think of the initial peaking time 100. So we don't peak before 100 for a sample size of 100. And what's maybe not that nice is, well, we have to peak infinitely late. So we look at the limit of m going to infinity. This looks a bit fishy, but if you look at the validity of confidence intervals, they're also only valid if a sample size goes to it. So that's the coverage guarantee we will have in the end. So you should peak late enough. And what we already see here, peaking late enough at M100 turns out to be almost a pain in the end. All right, so that's what I'm going to tell you in the next 45 minutes. So as these asymptotic confidence sequences are probably not that well known, I'll have a bit of a review. So let's start very easy, much too easy for a statistics faculty. So let's say we have IID data xi with the mean mu and variance sigma squared. Now, if you want to have a confidence interval that's valid at finite sample size, then you have that for all t in the natural numbers, the probability that mu is inside that confidence interval is larger than 1 minus alpha. That's the guarantee you want to have. All right, that's very nice. It even applies to sample size 2 or 1. Now, barely anyone is using that because it's very hard to construct such confidence intervals in practice. What we do instead, we often rely on asymptotic approximations by the CLT. So we don't want that for all t, but we only want that for large enough t, so for the limit of t going to infinity. Now that allows us to not know the distribution f, because if you want to do that, then you often need to know f. For this, you use the CLT. Fine. All right, now let's go to confidence sequence. So for confidence sequence, the for all operator moves inside the probability state. So here, you can only apply that at one fixed time. This probability must hold for all time points, but not for all time points uniformly. However, if you would have a guarantee like the one on the right-hand side, that for all t and n, mu is in the confidence sequence with a certain probability, then you can peek at the data every trading day. So now this is again a finite sample confidence. And there are contributions around, like how I've been showing around us. Now the problem, in my opinion, with that is, you again need very strong conditions on the F. Like you need strong conditions on the F, like you can construct that confidence intervals from Bernoulli data. There we know how to do that. That's 101. Similar constructions apply here. But now what we would like to do is make that big jump from finite sample to asymptotic validity that allows us to rely on the CLT. We would like to do that with the confidence sequences as well. And that's what this Warby-Smith et al. Paper did. And now the coverage guarantee here is a bit more involved, so this is very inaccurate and not mathematical. The probability that for all t large enough, mu in the confidence sequence is larger than 1 minus alpha. That's this limit over the peaking time we'll calculate on. Okay, so this is the object we want to go. Now, it's even not so clear, if you look at that, how you define that. So how you define this. And now the definition of an asymptotic confidence sequence in Warby-Smith et al. Is the following. So the sequence CSLU, so lower and upper bound, forms an asymptotic confidence sequence if there exists an unknown non-asymptotic confidence sequence. So one where we know finite sample coverage. This is the CS star. And for that, we know that the probability that for all t and n, the truth is in the confidence sequence is larger than 1 minus alpha. And we need that these two, that the limits respectively converge against each other. Almost surely. Now, it's a bit unclear on why should we define an asymptotic confidence sequence exactly like that and not maybe full cover. So why exactly that definition? Why do we need almost sure convergence? And if something like this holds, then do we get asymptotic coverages on something? This is not so clear from just that slide. And maybe let me say that in practice, we never know the CS star. So this just means there exists one, we don't know it, we don't even have to compute it. This is just a mathematical guarantee that if we come closer and closer to that confidence sequence, then we hope that we get a similar coverage guarantee aspect there. So now let's dig into these questions. So what we do first is possible alternative definitions of asymptotic confidence. So what you could start with is that, well, for classical confidence intervals, we have the limit or the lim-inf of the probability that the truth is in the confidence interval is larger than 1 minus alpha. Now you could say, yeah, okay, let's generalize that to the initial peaking time. So we have a for all t in m, and use in the confidence sequence. We let m go to infinity, so we peak infinitely late or very late, and then consider all times after the late peaking. Now this has to be larger than 1 minus alpha. So if you talk about initial peaking times, this would maybe be the most natural interpretation of such an asymptotic confidence sequence. But I admit, this is not that nice because we have this peaking time. Now, the problem here is that this probability in 1, this is always 1. This is not 1 minus alpha. For most of the asymptotic confidence sequences, this is 1. And I'll show you later why that is the case. So we have to do something here. So we need some additional details, and that is some tuning parameter, which we have to choose. We'll come to it. All right. Now, why almost sure convergence? Here, we have almost sure convergence, or not convergence, let's say, in probability. Now, if we dig a bit into probability theory, then what we need is convergence at all later times, because we want to have convergence for all times after the peaking time m. Now, you could say, all right, we have convergence in probability, we have convergence almost surely, we have convergence of all later times, almost surely, and convergence of all later times in probability. Now it turns out that these 3 criteria we have in red, they are all equivalent and stronger than this criteria. So, and the easiest from these 3 is almost sure convergence. So that's why we want to have almost sure convergence, because that implies convergence at all later times. What's a bit surprising is that this equivalence, what it holds. All right, now maybe let's discuss how can we actually construct such a confidence. And in order to start easy, let's see how we construct confidence intervals in the classical sense. So what do? Well, we look at the partial sum ST, and we approximate that by a CLT, by a Wiener process sigma W. So sigma is the variance. You could also put it there at the ST. Then we need to estimate that variance. We get a weakly consistent estimator, so convergence and probability we need. We get a pointwise confidence interval of that Wiener process or normal distribution. That's just the quantile you usually have in confidence intervals. And then we put all that together, the CLT, the weak law of large numbers for the variance estimator, and this normal quantile to get such a confidence. Now the construction for us is pretty similar, but a bit stronger. So what we need is, we have the same partial sum ST. We approximate it by a Wiener process, but now we need almost sure approximation. So while you have distributional approximation for the confidence interval, for that almost sure convergence case we need a strong invariance principle following Strassen and co-authors, or follow-up work. We need that. Now, of course, we need a strongly consistent variance estimator. Again, we need almost sure convergence. Then, instead of computing a pointwise confidence interval for the Wiener process, we now need a time uniform confidence sequence for the Wiener process. But how do we do that? I'll tell you in a second. And then we have to put everything together. And I'm also a bit vague how we do that. All right. So first of all, I would like to tell you a bit about these strong approximations. So what we have there is that we have almost sure convergence of a partial sum, of course under conditions, and the Wiener process, and that almost sure convergence rate is faster than square root t. This is a bit surprising because the distributional convergence rate is square root t. So how can that be faster? I'll show you in a second. Now these convergence rates vary a lot. And for example, these KMT approximations, they get the fastest convergence rate, but they need IID data. And we later on apply Kulps and Philip, and they do that for mixed. So we can get a classical time series setting it back. So very intuitively, what does the CLT say? The CLT tells, here we have a Brownian motion, many sample pair. Here we have the partial sum process. I think I simulated exponential distributions and then sum them up. Now, if we look at sample size 100 and plot the histogram over all these lines, and we plotted the histogram, we plot the histogram over these lines, then these two distributions are similar. That's distributional convergence. So histograms or the CDFs converge. Now, what's almost sure convergence? Almost sure convergence is the convergence on the path. So how you can think of that is, it's on the same probability space. You have one joint randomness. So think of a uniform distribution, IID 0, 1. Now, how do you simulate exponential data based on a uniform randomness? You can simply use the inverse CDF method. So you simulate the increments of the sum process ST as the exponential CDF inverted, and you plug in these uniform random numbers. Then you have an exponential distribution. And at the same time, you can simulate Gaussian random variables by using the Gaussian CDF to the power of -1 and plug in the uniform random number. And you take the same uniform random number. And if you do that, then you have simulated S and W, so both processes, on the same probability space, kind of, and by the same randomness. So the randomness underlying that is the UT. This is not exactly how the proofs work in these strong approximations, but that's at least how I think of it. I hope it's correct enough. So what that means is that if you plot that for one realization, so for one path of realizations, omegas, for these UTs, then you get these two processes in blue and red. For the second realization like that, and for the third like that. And these processes are close together, and by that rate, which is even a bit faster than square root t. So it doesn't really contradict the CLT in the sense that, well, if you have a faster rate than square root t, then what about the CLT? So this is simply a different notion of convergence, and that's why we're going. So if at any point you want to ask something, just go ahead. I forgot to tell you. All right. Now let's talk about boundary crossings for Wiener processes. So let's say we have a Wiener process WT. Now there are old results from Robbins that for any row greater 0, the probability that at any time t and n, the Wiener process exceeds that boundary is larger than 1 minus alpha. So this is kind of a uniform boundary that you can have for the Wiener process. And the probability that the Wiener process exceeds that boundary at any time point is small or bigger or equal to 1 minus. If you would have all t in the real numbers, then you get equality. So what do we see here? There's this tuning parameter rho. We have to talk about that. This parameter is more important than you might think. If you want to know how that scales in t, it scales as square root t times ln t. So it scales a bit wider than the classical confidence intervals that scale with square root t. And it grows very slowly with alpha as normal confidence intervals because they have the square root of logarithm of 1 over alpha squared. All right, so let's talk about this tuning parameter rho. Now, what I did here, I plotted that boundary in color for rho equal to 2, 10, and 10,000. And as we saw here, this holds for every row individually. And now you see these bounds are quite different. And now what you can say is you can optimize the minimal width of the boundaries. So you can solve that, you can minimize that width by rho. And then you get for rho equal to 2, this has minimal width at t equal to 2. I normalize time to 1, so t equal to 2 would be here. The green one has minimal width somewhere here, and the blue one has minimal width here. So you see that it's not that the violations are distributed uniformly through time, but almost all violations, so points where the gray Brownian motions, these are 50 sample pairs of Brownian motions, where they lie outside of the blue band, they're almost all in that region, but not here. You see the distance is quite. So in that sense, how you specify that parameter is quite important, because if you start peaking here and you use the blue band, then you already see why the probability that you're inside is 1 and not 1 minus alpha. Because if you peak late enough, you always exceed that time at some point. So that's this counterintuitive statement about probabilities being 1. However, what you can do, you can kind of tune your confidence sequence to have minimal width just after the initial peaking time. So for example, if I would like to start peaking at my data here, then maybe the green band isn't so bad because it's relatively tight in that region. That will be the end later on, the idea later on. All right, so that gave us all the tools we need to now really talk about sequential evaluation of predictive ability. So now comes the literature slide that I still haven't shown you. So for the people working on predictive ability, we all know these classical fixed time tests, Diebold, Mariano, Giacomini, White, there's a Lai et al. Paper about that and so forth. So this could go on. Then there are just a few papers about time uniform tests, exactly what we are trying to do. That's one of Hensley and Siegel. They are restricted to the setting of binary probability forecast for binary events only. So does it rain later on, yes or no? This is very restricted. And there's this Cho and Lambdas. They look at finite sample valid confidence sequences, but the trade-off for these finite sample validity is always that you have to have strong distributional assumptions. So what they use, they say my loss differences are bounded or sub-Gaussian, and then they can do something. However, the problem here is this, first of all, it gets very conservative. And second of all, for example, if you compare volatility forecasts, the loss differences are unbounded. because you cannot put a bound on the financial return tomorrow. You don't know. It's definitely below that bound. Then we compare against that in simulations later on. Then we build on the theory of asymptotic confidence sequences of that Warby-Smith et al. Paper. And this paper is part of the fast-growing literature in safe and anytime valid inference that's developed in the last 5 years, I would say. I cited a book about that. And then what we did not consider yet, but it might be possible that it's generalizable, are all these predictive ability generalizations to multiple forecast comparison, estimation, error in the sense of rest, score decompositions, then calibration optimality, and whatever you want to think of. So now let's do a bit of new notation. That is that I will use for the rest of the talk. So the loss differences that we observe, that will be delta I tilde, hat, and they have expectation delta I. So delta I is the population part, delta I tilde is the what we observe part. Now we look at accumulated means. So we look at the sum from I to 1 up to time t, that is today's time t. We sum over all the past. If you sum over the empirical small deltas, then you get the empirical large delta, and if you sum over the, if you take expectation, you get the delta t. Yes. So we have small delta loss at a time, capital delta loss of all past, average loss of all past data. Now we don't need stationarity of delta I. This is quite nice. So we can actually talk about time varying predictive ability. However, at least now we can allow this delta I to vary, but it must stabilize asymptotically. But the reason we need that is only for the Hug estimator. So we have ideas how this could be done a bit more general by using a different variance estimator, but more later on. Now, I show you again our asymptotic confidence sequence. That CT is the running mean plus the variance estimator times that bound of the Wiener process we have discussed already with that rho. And now for any rho, you can show that this is an asymptotic confidence sequence. So in the theorem, we say this is an asymptotic confidence sequence for delta t, meaning that delta t is in there often enough. But so far, this only means that, well, there exists a non-asymptotic confidence sequence and they converge against each other almost. And what we need is, we need that the difference of delta I hat and delta I is stationary in alpha mixing. We need that for the stronger approximation of Cope and Philip. We need some moment condition that we usually need, and we need almost sure convergence of the Hug estimator. So if you have these three conditions, you know it's an asymptotic confidence. All right. Now, remember the coverage problem. So in the asymptotics we want to look at a limit where the initial peaking time converges to infinity, m goes to infinity, and then we peak at all time points t larger than the initial peaking time, and then that Wt stays below that threshold. I told you this is 1. This is not 1 minus alpha, this is 1 for all alpha. Now the reason is simply that, well, if I use the blue band and I start peaking late enough, let's say here, I never have any violation on that part. If I use the green band and I start peaking here, I never have any violation. And if I have the red band and I start peaking outside on the floor, then I never have any violation. So I somehow have to connect this rho with the initial peaking time. And that's exactly what we do. So we use the band with a rho m that has this, which looks like that. So it's a constant c that we even know, we can compute it, divided by m ln m, and this m ln m. So this peaking time results in a confidence sequence that has minimal width at m ln m. So a bit after m. So if m is 100, then m ln m is maybe 400. So we have minimal or small width after we peak. And now if we simply plug in, instead of rho, we plug in rho m in that confidence sequence here, then we get exactly the right coverage we want to have. So we get that the limit, initial peaking time diverges, of the probability that for all t large to m, the truth is in that confidence sequence is exactly 1 minus alpha. So we could resolve that puzzle by just peaking late enough. All right, now this is the main theory we have. Now I only show you generalizations or something, but it will not get much different. So one thing is one-sided asymptotic confidence sequences. Now, if you think of one-sided confidence intervals, you just increase alpha, or like you change alpha to alpha over 2. That's all you do. Now, the problem here is, when we go to a plot, it might be that this Brownian motion first diverges over the blue band here, and then later over the lower band. This is not possible in a fixed time setting. because your sample average can either be above or below the confidence, but not both. But here it can first, at some point, be above and then below. So these events are not destroyed. And we have to adapt a bit more. So what you do here, the only change is this red function. Before that, this red h to the power of -1 is the inverse of that. So of z squared plus 2 times ln of phi of z, that's the standard CDF of a normal distribution. Now the two-sided case arises for the inverse of z squared. So if this h to the power of -1 is a square root, then you're in the two-sided case. For the one-sided case, well, you have to do a bit more. So you have to take into account that violation below and above can both happen in one omega realization. All right, but you already see that z squared grows much, much faster than ln of phi of z. I mean, phi of z is bounded by 1 anyway. So this only matters in the first few observations, but where it really matters, it's almost the same. So this is not really big. All right. Now, I've shown you tests for unconditional predictability, and I would even argue that tests for unconditional predictability are more important than tests for conditional predictability. You might disagree. The reason is that most researchers actually apply tests for unconditional predictability, and even when people, or most people citing Giacomini White for conditional predictability, actually use unconditional predictability. So what do we do now? So our object so far was simply the expectation of our empirical loss differences averaged over time, so that delta t. Now what we use in conditional predictability is we have a delta t c for conditional, and that's the average over all these delta t's, however, conditioned on some past information fi minus 1. So you condition on an information set that's known when the forecaster was issuing his or her forecast. All right. So can we also develop asymptotic confidence sequences for that? Now, the answer is it's even easier here. And the reason is that this STC is a martingale. So the difference between delta I hat and the conditional expectation turns out to be a martingale. So how do we do that? Well, quick proof. So we write the conditional expectation of STC, conditional on ft minus 1. This is simply definition put in there. Now we split the last element of the sum and take it out of the sum. That's this guy. And all t minus 1 elements of the sum. It's classical martingale proof. So we see this term is simply st minus 1. And this guy has mean 0 because the delta tc is exactly defined as that conditional expectation of that guy. So you quickly see this is a martingale. Now this whole Savi literature is built on martingales. So in this case, we don't need a Huck estimator, and it works a bit easier. And that's actually what Cho and Randers do, more or less. Now you can already see this breaks down for multi-step ahead forecasts, because then you don't have a martingale anymore because you would condition on ft minus h. So this only works for one step ahead. Okay, now we have a simple variance estimator, not the Huck, so we don't need the cross terms. And the confidence sequence looks a bit different. And just this or last week, we figured out why, to be honest. So now you have the variance estimated in the square root and in the logarithm. So you would think, okay, why does the variance estimator before? We just had a sigma before the square root. Now I will come to that in a second, why it looks a bit different. Now we use, so this guy is an asymptotic confidence sequence for delta tc. And now if we use that rho m, so that tuning parameter based on initial peaking time, which now also contains the asymptotic, this variance estimator, then we know that the respective confidence sequence also has that asymptotic coverage. And well, if you would plug in that rho m in there, then this variance estimator would cancel with that one. That's why it looks a bit different. So that's essentially only a reparameterization in terms of that rho m. So this is non-essential. It looks different in the beginning, but it's not. Okay, but you can also do it at least for one step ahead forecast for conditional predictability. And you can, of course, combine that with the one-sided case if you want to as well. All right, yeah, sure.
But then the question would be why to put the variance that picky?
Yeah, we figured that out last week. And we're thinking of kind of aligning it in the page. So that was something I was always asking myself when I was anticipating the question, why does it look different? So I thought a bit further about it, and then we discovered, yeah, well, okay, kind of cancels it. All right, now the, I would say, strongest competitor in terms of time uniform inference is this Cho and Randers paper, and they assume that loss differences have a known bound delta E hat smaller than C. So for example, if you look at binary events and you use the MSE, the prior score, Then you look at forecast, which is a value between 0 and 1, minus outcome, which is a value 0 or 1, and square that up. This is always smaller than 1 in absolute value. However, if you use the log score, then this can be infinite or minus. So this is a pretty restrictive condition. And for example, for mean forecasts and the random variable you're trying to forecast is unbounded, then no strictly consistent loss function is bounded. So this is a very serious. And what they do is they have finite sample valid confidence sequences. So finite sample valid is nice. It means they're not only valid after waiting quite long till you can peak, they can peak from the first day and they still are valid. However, they look pretty similar to what we do, but this constant C is the upper bound here. And you can already see we put an estimated standard deviation. Now, this estimated standard deviation makes it much, much smaller than the known upper bound. So if you know you have an upper bound of 10, then the standard deviation can be 1. And so our confidence sequences are much thinner just by observing that. Well, they can only look at one step ahead forecasts because otherwise this STC is no longer a martingale. What they do for multi-step ahead forecast, there's a proposal in the appendix. They look at spaced subseries. So if you have 3-day ahead forecast, then you look at day 1, 4, and 7. Look at that sequence, look at day 2, 5, and 8. So then in that subsequence, you get a martingale. In that subsequence, you get a martingale and that. And then you have to combine the evidence across all series. But then you have to take the maximum of p-values, and this is awfully conservative. And we will see that. And so this proposal is quite conservative because of 2 reasons, this bound C and this multi-step ahead combination. So let me quickly show you some simulations. In the first one, we use an AR1 loss difference. So we directly simulate the AR loss difference process. This has a coefficient of 0.1. We can increase that, of course. It gets a bit worse, but I think the main reason for that is a Huck outcome. We look at 95% confidence intervals and the asymptotic confidence sequence, and we consider 3 initial peaking times, 10, 100, and 1,000. Because in practice, you would like to know, well, we have this asymptotic guarantee for m going to infinity. Can we peak after 10 days, after 100, or only after 1,000? This is how one simulation run looks like. So we have the confidence interval in here. This is, of course, smaller. Then if we start peaking at day 10, we have this green interval. And this goes up to infinity. Then if we start peaking at time 100, we have this red interval, which is a bit different from the green one. And we have the blue one, purple one, which is still, I think, a bit wider than the other. Because if you peak later, I don't even know that's true. But you see, these are pretty similar at some point if you peak later. Now, if we look at cumulative miscoverage rates, so that means how often was the truth outside of the confidence interval at any time point t larger than the peaking time. That should be alpha or below alpha. And so what we see for the confidence intervals, starting peaking at 10, 100, or 1,000 is quite bad. In the end, at sample size 10,000, we end up at 30, 50, or even 70%. And for our intervals, our sequences, it looks much better. So if you peak at time 1,000 for the first time, then you're even below the nominal level. If you start peaking at 100, you're just at the level at 10,000 or maybe a bit above. And of course, if you start peaking too early at m equal to 10, then you also have problems. But I think much of that is that you compute a Huck estimator with a sample size of 10, and you wouldn't do that. So you wouldn't start comparing forecasts after 10 days. So I would say that you're allowed to start comparing forecasts after 100 days is already quite good. So this asymptotic validity doesn't hurt us that much because it turns out to be okay. And now in order to compare against Cherry and Ramdas, we again have a very easy simulation setup. So we simulate IID Bernoullis with a hitting percentage of 0.5. We have one perfect forecaster that always forecasts 0.5 and one suboptimal forecaster that forecasts 0.25. And we evaluate with the MSE or prior score so that the loss differences are bounded. We can use their method. Now they test conditional predictive ability, we unconditional. But it's actually the same thing because there's no conditioning involved here at all. So in that sense, it's more or less comparable. Now what we see is the following. So on the right-hand side in black, we have our cumulative rejection probability, so power. We don't have any power up to, so we never reject up to day 100 because we haven't peaked at the data up to day 100. And then our power shoots up quite fast. And at sample size 250, we have a power of almost 1.95. Now, if we look at the Sherwin-Ramdas proposal, they can start peaking from day 1 because they have finite sample validity. Now, for leg 1, their power increases as well quite nicely, but For 250, where we had 95% power, they have 30% power, and even at sample size 500, they have something comparable, 95. And then you see that taking the maximum over the p-values of all these spaced sequences, this deteriorates power quite fast. So at lag 4, you don't have any power at lag 1000. And for us, different lags are treated exactly as. So we kind of get the lags for free because we don't need a martingale, because that's taken care of by this asymptotic consideration. All right. Now, very quickly, a short application. I have to admit that this is very early work in progress, so I put together a short application last week. So I looked at 20 years of S&P 500 returns, used the last 1,500 days for forecast evaluation. 3 methods: historical simulation, a Gauss normal model, a GTL Gauss T model, and we evaluate by MSE and Q-like loss. So another famous loss from volatility forecast evaluation. These are our forecasts and returns. So in gray, the returns. In green, that's this plateau for the historical simulation you saw in the motivating example. And the Gauss models perform much better, I would say. Now, what we do here is let's focus on first in this plot, because that's the plot we had in the motivating example. So we have the empirical loss difference in blue, the Diebold Mariano confidence interval in black, and our confidence sequence in red. You can see that it's a bit wider, but you can reject even while monitoring continuously. And for example, if you look at other pictures like the Q-like norm versus GTR gauge, there you see that, well, our red band cannot reject the null hypothesis for any days before. So I'm not claiming a lot of new knowledge in that. This is just an application that you see how it works in data. All right, now let me conclude what we do in that paper. So we propose predictive ability tests that are time uniform through the new theory of asymptotic confidence sequences that allows for time uniform inference, meaning data peaking, at least if you peak late enough. That means we can draw conclusions as early as possible. So you can look at the data every day and kick out a forecasting model as soon as it performs not on par with the other models. We can handle unbounded short difference and multi-step ahead forecasts, which was not possible in that literature before. And we can do 1- or 2-sided asymptotic confidence sequences for both conditional and unconditional predictive ability. In simulations, we see especially drastic power increase over Turing lambdas for multi-step ahead forecasts. So thank you very much, and I'm happy to initiate a discussion.